In a legacy, flat Layer 2 network, every device shares the exact same physical environment. If you plug a cable into a switch, that machine is immediately exposed to the traffic of every other connected machine. The baseline limitation of this physical topology is that a single switch, or even a series of connected switches, creates one massive shared broadcast domain. This creates an immediate operational burden. Basic networking functions rely on broadcasts, like ARP requests asking for MAC addresses, or DHCP discoveries searching for IP assignments. In a flat network, every single connected host is forced to receive and process these unrequested frames. As the physical infrastructure scales to meet enterprise demands, the volume of this background noise grows. 10 devices shouting over each other is manageable. 10,000 devices doing it simultaneously creates a broadcast storm that can overwhelm host CPUs. Network response times severely degrade when broadcast traffic exceeds 1,000 broadcasts per second per logical segment. At this threshold, the bandwidth required for actual data transfer is consumed by the overhead of administrative chatter. The solution relies on abstracting the physical hardware. Administrators logically group specific switch ports together, mathematically containing the broadcast traffic within dedicated boundaries. These logical groups are called virtual local area networks, or VLANs. They allow you to place a workstation in the finance segment or the human resources segment, regardless of where that specific device physically connects in the building. Isolating a noisy network segment prevents its administrative chatter from bleeding out and consuming the bandwidth of the entire campus infrastructure. A broadcast generated in finance only reaches other finance ports. Decoupling the physical wire from the logical topology is a survival necessity for enterprise scale. Without this mathematical separation, large networks struggle to maintain performance under the weight of their own traffic. This logic extends directly into network defense. Logical isolation is the mechanism used to keep unauthorized users out of sensitive databases. Modern architecture relies on the zero trust model. No device is trusted by default. The fact that a workstation is physically located inside the corporate headquarters grants it no inherent privileges to access other segments. In a flat network, a threat actor who compromises a single reception desk computer can pivot to accounting servers or engineering workstations instantly. Research indicates that attackers can begin moving laterally across devices in as little as 14 seconds after an initial breach. VLAN segmentation acts as the baseline quarantine barrier. If an attacker breaches the reception VLAN, they cannot reach the accounting VLAN at Layer 2. To cross that boundary, their traffic is forced through monitored Layer 3 firewalls, where it can be inspected and blocked. These Layer 2 boundaries form the foundational isolation layer of a zero-trust environment. By confining a breach to a single segment, defenders gain the vital window of time needed to identify and contain the threat. Multi-vendor segmentation is made possible by a specific open standard protocol, IEEE 802.1q. The protocol solves a mechanical problem. A physical switch ASIC operates at wire speed. It needs a hard-coded trigger to recognize abstract logical boundaries without slowing down traffic. This diagram illustrates a standard 1518-byte Ethernet frame with its source MAC address and ether-type fields. 802.1q achieves logical separation by injecting a 4-byte header exactly between them. As a direct result, the total frame size increases to 1522 bytes. When this tagging protocol was first introduced, legacy equipment would read the 1522 byte size, classify it as a malformed giant frame, and drop it. The IEEE 802.3ac standard updated hardware tolerances to accept these larger payloads. The routing power of the 802.1q protocol exists entirely within the internal binary structure of that inserted 4-byte tag. This matrix isolates the first 16 bits of the tag, designated as the Tag Protocol Identifier, or TPID. The TPID carries the hexadecimal value 0x8100. This value acts as a mandatory hardware trigger. The moment a switch reads 0x8100, it knows the frame is tagged and is forced to process the remaining bits as control information. Global enterprise segmentation relies on hardware universally recognizing and reacting to this exact 16-bit sequence. The remaining 16 bits form the tag control information. This section splits into subfields dictating how traffic is prioritized and where it is allowed to go. The most critical is the 12-bit VLAN identifier, or VID. This strict numerical address specifies the frame's logical destination. Because the VID is exactly 12 bits long, it creates a hard mathematical constraint, supporting a maximum of 4,096 possible logical IDs. Due to operational reservations, VLAN 0 is held for priority tagging, and VLAN 4095 is kept for management tasks. This leaves exactly 4,094 usable network segments for standard data traffic. Moving down the header, we find the 3-bit priority code point, or PCP section. VoIP infrastructure relies on these PCP bits to prevent jitter. By applying a specific value in these 3 bits, a switch is instructed to prioritize sensitive voice traffic over standard, delay-tolerant data packets. These 16 bits of control information are the specific mechanism used to enforce departmental isolation and prioritize real-time traffic across a shared network fabric. To understand how frames are processed, we must look at the specific switch hardware interfaces handling the traffic, which are divided into 2 distinct configurations. Access ports act as the boundary edge of the network. They are dedicated strictly to connecting end-user devices, like a workstation or a printer, to the network fabric. Access ports follow a strict traffic handling rule. They only process and emit standard, untagged Ethernet frames. When an untagged frame hits an access port, the switch ASIC internally applies the correct VLAN tag. Before that frame exits another access port to reach a destination device, the switch strips the tag away. The process remains invisible to the end user's host. Trunk ports serve an entirely different purpose. These are the high-capacity backbone connections linking switches and routers to one another. In a large enterprise, it is physically and financially impossible to run a separate physical cable between switches for every individual VLAN. Trunk ports utilize the 802.1q tags to multiplex traffic safely across a single shared physical medium. As data passes over the trunk link, the hardware reads the inserted tags to ensure every frame stays in its designated logical lane. Access ports hide the complexity of segmentation from the end user, while trunk ports enforce the logic across the broader enterprise. There is one operational exception built into the 802.1q trunking protocol, the native VLAN. By definition, the native VLAN is the single segment on a trunk designed to transmit and receive frames completely untagged. It operates on an automated assumption mechanism. If any untagged frame arrives on a trunk port, the switch automatically categorizes it into the native VLAN. Hardware vendors traditionally default this to VLAN 1. This allows management protocols, like the Cisco Discovery Protocol, to establish communication lines without requiring manual configuration from the administrator. This plug-and-play convenience comes at a cost. The native VLAN exception introduces an exploitable blind spot in zero-trust architectures. Logical boundaries are fragile. Layer 2 isolation can be compromised without an attacker ever touching a firewall or attempting a complex decryption. The first major exploit vector targets the dynamic trunking protocol, a vulnerability known as switch spoofing. Administrators sometimes leave user-facing switch ports in dynamic desirable or dynamic auto states, relying on the hardware to negotiate the connection type automatically. Threat actors use packet generation tools to exploit this trust. By transmitting specific DTP messages, they trick the port into negotiating a direct trunk link with their workstation. Once established, their laptop gains access to all permitted VLANs on that link. Automation protocols designed to save administrative time are often the primary entry points for catastrophic Layer 2 compromise. A more sophisticated method is the double tagging attack, which explicitly exploits the untagged rule of the native VLAN. An attacker injects 2 stacked 802.1q headers. The outer tag matches the native VLAN ID. The first switch reads the native tag, strips it, and forwards the payload. The second switch reads the exposed inner tag, routing the packet into a restricted network zone. Because this lateral movement executes entirely at Layer 2, higher-level Layer 3 firewalls remain completely blind to the transaction. Exploiting protocol rules turns the network's own hardware into a tool for the attacker, as the switch flawlessly executes compromised instructions. Systemic defense against Layer 2 hopping requires rigorous manual configuration of the individual switch ports. To prevent switch spoofing, administrators must explicitly define user-facing interfaces as access ports and universally disable DTP negotiations. To stop double tagging, migrate the native VLAN from default VLAN 1 to a completely unused segment where user access is impossible. Additionally, administrators execute VLAN pruning. By manually restricting trunk links to carry only strictly required traffic, you cut off unnecessary pathways and minimize the attack surface. Active monitoring is also required. Using discovery protocols to detect native VLAN mismatches across endpoints prevents spanning tree instability and blocks accidental data leaks. VLANs provide the illusion of physical isolation, but their integrity is purely mathematical. The boundary exists entirely within the specific arrangement of the 802.1q header. A resilient, zero-trust enterprise network is built through the disciplined execution of foundational switching protocols. Security at scale begins at the port.